Now to today's presentation. Today we're pleased to have Sаймонд Jones join us as our presenter. Simon is a chromatography applications engineer located in Agilent's Folsom, California site. His current responsibilities include providing technical support for Agilent's North American GC column customers, as well as support resource for GC applications and other consumables. We're ready to begin today, and it gives me great pleasure to welcome Sаймонд Jones. Simon, you may begin.
All right, thank you, Rita. Welcome, everybody, to today's presentation. Just to forewarn you, there are a lot of slides in today's talk, but I did that purposely in part to provide just reference material for you, since you do get a copy of the presentation after today. You will have it on hand, and again, there's a lot of useful information in there, and so much so that I won't be able to go in depth with a lot of that as we progress. So, again, if there's things that you see that maybe I skip over briefly, you can always ask a question at the end, or I've provided the ways to get in contact with myself and my group at the end as well. So again, if you do have any questions, feel free to either ask right away or call in. So as we get going, as you develop a method, and this is going to be true for any analytical method, the things that you need to consider are going to start with the sample, obviously. We got to make sure that it's actually going to be amenable to the type of instrumentation that you want to use. When it comes to GC, of course, then we have ways of getting the sample into the system. So our method of injection we have to consider. The inlet, the type, the parameters, and things like that also are very important, as are detectors. And again, we're going to hit on all of these as we go through, and I'll kind of give little stories maybe of instances in helping people out with choosing an inlet or detector and some things that if you don't consider, you're not going to start off being successful. And we'll also talk briefly about the carrier gas as well as the column. And we have actually a whole talk on just selecting the right column. So I'll go over that just a little bit briefly, just to give you an idea of, or maybe things to think about as you decide, how to attack your next application. So the compound requirements for GC, really only about 10 to 20% of all compounds out there are even suitable for GC analysis. The two things that really kind of govern that are going to be that they have to be sufficiently volatile, and they also have to be thermally stable. So you don't want anything to decompose or degrade when it's either on the column or even getting to the column. And with certain applications, that is actually a problem. Really the only things that you want to kind of stay away from would be any inorganic bases and acids and bases, and then of course, if you neutralize things, then you're going to create salts, and those aren't volatile, and those can stick around and create some issues for you as well. So when we think about the samples, then be mindful of the matrix. Everything's going to have residues. Standards have residues and things like that. So we have to be mindful of that and be able to address that, and not be surprised all of a sudden if we start to have some issues arising. We almost have to suspect them at some point. Again, if you have really, really clean samples, maybe you go a couple thousand injections without any issues, or if you have really dirty samples, maybe you go 10. So that's, again, some things to think about. And then, of course, the analyte composition. And this is going to be more driven potentially by, what kind of column do we need? Again, mode of injection and detectors and things like that. Do we have isomers? Are we dealing with light gases? Are we going to be injecting it then with a gas sampling valve? Maybe we need to use a plot column instead of a wall-coated column. And again, I'll go over some of those here in a little bit. So we need to know a lot about our sample. Oftentimes people call up, say, hey, I want to analyze methanol. So, okay, well, that's great. That's really easy. You can use just about anything. The real question is then, what else is in the sample? What do you need to resolve the methanol from? What's the matrix? We have to consider all of that through the whole, decision process, inlet parameters, column type, and things like that. So, again, really consider all aspects of your sample. When dealing with the residues, what can we do with them? If they're semi-volatile residues, we can either bake them out, have an extended hold temperature at a extended high hold temperature. Sorry. At the end of a run, maybe we can, with some of the new devices, we can do a backflush and throw them back out the inlet. Non-volatile residues, we could use a guard column, just provide some surface area for them to fall out on, so we're not throwing away an analytical column quite as often. Again, maybe backflush. If they just get in there, it should be simple enough to push them right back out before they migrate anywhere. And then, of course, if we have dirty samples, sample cleanup. Can we take some time to do that? Of course, everybody wants to just inject things and get an answer and go about your business. But depending upon your sample type, again, you may be able to get through 10 samples, and then you've got to spend 2 hours cleaning and doing some maintenance on your system. So if you can spend 5 minutes on sample cleanup initially, that's going to really help you out in the long run. And with that, I have my sample prep colleagues had asked to say a little bit of stuff in there since it is so important in your whole application. It can, again, do sample preparation. And one of the things that you can see here, and again, I'm just going to kind of brush over this, is that there's some pesticides in avocado without any sample prep. And so you can see here's your peaks of interest, but here's the matrix background. So you're trying to get a signal from the kind of a signal of noise behind it. And as you do your sample cleanup, you can see that things get a lot easier to quantitate, and you also get a lot better signal to noise. So you can have lower detection limits. Things are easier to see if you can spend that time to clean things up. And of course, if you're not getting all that junk into your column and into your system, you're also going to end up doing a lot less maintenance over time. So it's a benefit in more than one way. So we have a whole bunch of different sample preparation techniques. And as you go from this list here, the selectivity, complexity, and cost does increase. So you have your syringe filter. So if you have sediments and things like that, you can take 2 seconds, put it in a syringe, squirt it through the filter into a vial, and then load it onto your system. And then we have some other participated proteins that you kind of push out of the sample. Then we have a dispersive solid phase extraction, which is the catchers, which I believe is quick, easy, cheap. I forget if it's environmentally friendly or effective. Excuse me, that's what effective, rugged, and safe is what catchers stands for. It's a very quick, effective way to clean things up. Again, if you want better cleanliness out of your samples, then solvent exchange, extraction, and then, of course, your solid phase extraction is going to give you the highest level of cleanup. And again, that's going to affect your sensitivity. And here, again, catchers is nice and quick and easy to utilize. And then we have something new, which is our enhanced matrix removal, which works with catchers. So that actually depletes some of the background materials, proteins, and things like that may kind of come through even with the catcher's extraction method. And as you can see here, these are all varying. It's kind of a messy slide, but you can kind of get the idea is that here's with our enhanced matrix removal system with the catchers, you can see on the red line that it's a lot cleaner than with the C18, some of these other types of cleanups. And again, you're just keeping all this stuff out of your sample, off of the column. And then it also helps, obviously, if you have analytes of interest that are buried within this mess, it's obviously going to be a lot easier to find those on a nice clean baseline. And granted, a lot of people are using, SIM mass spec or triple quad, so they're basically filtering all this out from the detector side. But this is all still going through your column, and it is going to affect your analyte of interest. So, again, developing your method and things like that, you may have a way to filter this out with the system, but it's still in the system, and we are going to have to deal with it at some point in time. So now that we've actually spent some time considering the sample and thinking about cleaning it up and things like that, what do we have to do next? Well, next, obviously, if we have the sample prepared, we got to get it into the system. And with that, we can do manual injections. We can do a liquid injection with an auto sampler. Nice, clean method of injections, headspace, as well as purge and trap. If we're dealing with gaseous samples, we may have a gas sampling valve. Or, again, we want something clean. We have a solid phase micro-extraction, thermal desorption, or some type of custom build that gets our sample onto the column and into the system. So depending on what your method is, again, you have a whole slurry of different types of injection methods that you can do and take advantage of. And again, you may be, liquid injections are nice and easy, but maybe the sample type that you have, again, if you have salts or you have some nasty stuff, headspace may be an option for you. If you have volatile analytes, you can use headspace. You avoid getting any of the garbage onto your column, and, you ultimately end up doing a lot less maintenance if you have a headspace as your mode of injection. Then on to the inlet, and of course we have a whole flurry of different inlets that we could use as well. You have a volatiles interface, we have cool on column, we have purge packed, PTV, which is programmable temperature vaporization inlet, splitless, which is the most common one, and then we have a multi-mode as well, which is kind of a combination of a splitless and a PTV inlet all in one, so it gives you a lot of flexibility. And as we go over these next few slides, this is where I'm going to kind of brush over things because I give a lot of information on these various different types of inlets that, again, you may want to look at in greater detail away from the talk. So the volatiles interface is usually used for headspace and purge and trap. It's basically just a throughput for your sample to go from the transfer line of either one of these auto samplers, basically to your column. So it really has a very minimal flexibility. Again, here you can see you can run it in split and splitless and direct, but you can't, in troubleshooting instances, you can't really do manual injections into this type of inlet. So it does limit your flexibility, but it does have its utility as well. And as we move, we have a cool on column inlet. This is very good for labile samples because you're actually injecting into the column. And of course, if you're considering sample expansion as you inject into a hot inlet, and again, we're going to get into that a little bit more in detail with the splitless inlet. With a cool on column inlet, again, we want it cool. We want it below the boiling point of your solvent that you're using, and you inject it directly onto the column, so you're not getting your sample in contact with a liner or any metallic parts within the inlet itself. It's going into the column very gently, raise temperatures. It also is good because since your sample is all being injected onto the column, you have no inlet discrimination. So if you have a wide range of compounds, say you're just even doing a hydrocarbon analysis from C5 to C60 or 80, all of that material is getting onto the column. So it's a lot easier to get that C80 out to the detector versus using a splitless or vaporization type of inlet. Purge packed inlet. These are good for high flow applications. This is why it's usually for a packed column, but you can use them with a 0.53 and a 0.32 ID columns. Smaller ID columns do suffer chromatographically, and that's basically due to the volume at which the sample is swept through the inlet. Again, with a purge packed inlet, all you have is your column flow. So the smaller IDs have a smaller volumetric flow to push the gas through there. So your sample moving through the inlet moves a lot slower, gets onto the head of the column a lot slower, focus is not nearly as good, and you could start off with broad peaks. So if you do have a purge packed inlet, an older cistern or something like that, and you are converting over to a capillary column, my recommendation would be generally to look at a 0.53. It's not as efficient as a 0.32, but you can get your sample loaded on the head of the column a lot more quickly. One of the things in doing so is that since it has minimal capacity, only about 170 microliters of vapor volume in the inlet, backflash is definitely a problem with capillary columns in the purge packed inlet. Then on to the PTV, programmable temperature vaporization. This is good for large volume injections. This is also a temperature cooled injection. So you can, again, put your inlet temperature down to again, even down to negative 160 if you wanted, basically freezing your sample in the inlet. Bring the temperature up ever so slightly, vent off all the solvent, or most of it, and then ballistically heat it up and drive all your analytes of interest onto the column. So it does, again, have a lot of benefit that way. And you can run it in hot or cold and split or splitless. So, again, a little bit more flexibility than some of the previous inlets as well that we said. Again, here it's going to give you a little bit of kind of tabulated on where you can use it and what the benefits are. And on to the splitless. We're going to spend a lot more time talking about the splitless and the parameters used with this just because it's the most commonly used inlet. Many of you know that you have split mode and you have splitless mode, but you may not know that you also have a pulsed split and a pulsed splitless option with that too. And again, going through the next set of slides here, we'll get into why this can actually be beneficial for your application. So when we consider a split mode for the splitless inlet, there are things to consider. Is that we're too low of a split ratio. We have poor peak shape. Again, this goes back almost to what I was saying with the purge packed inlet in the volumetric flow through the inlet and pushing the sample onto the column. If we go too slow, again, we're going to have broad sample loading onto the column, which is going to lead to broad peaks and things like that. So typically the benefit, and this is where you'd want to start if you're doing an application that you know that you may end up in splitless mode, I would suggest always starting in split. At least a 20-to-1 split. It's an efficient mode of getting the sample through the inlet onto the column, so you can really dial in your chromatography and then scale things back if you need the sensitivity. As I mentioned, too low can give you poor peak shape. You can get overload, depending on what the concentration of your analytes are. Too high, obviously you're going to have poor sensitivity because you're going to be venting out a good portion of your sample, and you're also blowing a whole bunch of carrier gas out there. You can basically push 900 milliliters per minute of carrier gas out your split vent. If you have a 150, 200 to 1 split ratio or something huge like that. We do have an option on the GCs called gas saver. And if you've been curious on what that is that will take your high split flow and basically dial it down after a minute or 2 minutes of your analysis. So after you've loaded the sample on the head of the column, you click the gas saver on, you go from pushing 200 mils a minute out the split vent down to 20, so you're saving gas. The split is a non-linear. As you could test this yourself, do not use this ratio as a dilution factor. So if you're at 10-to-1 and you want twice as much sample, you drop it down to 5-to-1 as your split. You may see that for some analytes, but I'll guarantee that you're not going to see it across the board for your whole sample. Just the dynamics of how the flow goes through the inlet is not always the same, nor is how each analyte is treated within the inlet. With a smaller ID column, you typically want a higher split ratio. And again, this comes through the whole volumetric flow and efficient transfer of the sample through the inlet. The smaller the ID column, the slower the volumetric flow that you're going to use with that column. So typically, again, with a 0.1, you're going to want a really high split ratio just so you can get the sample transferred from the inlet onto the head of the column. You may be thinking, going from a 0.53 with a really low split ratio down to a 0.1 with a really high, that you're suffering because you're going to be venting a lot of your sample out, which is true. But the smaller the ID column, it's much more efficient. So your peak shapes on this is going to be so much sharper than they would with a 0.53 ID column that you can actually put less sample on the column and still have the same sensitivity. So that's another thing to consider as well. If you have small amounts of sample, maybe you do want to inject less sample onto the column. Choosing a smaller ID column may be something that's going to be appropriate for you. As a rule of thumb, really what you want to shoot for is having a roughly about 20 mils a minute of flow through the inlet. So that's going to be your column flow plus your split flow. So if you got 1 mil a minute of column flow, you're going to want roughly a 20-to-1 split ratio so that you're right roughly at that 20 mil a minute through the inlet itself. I mentioned, the multi-mode can do the function of the splitless inlet, and then it has also solvent vent and direct, which is more like a PTV. So this would enable you to do the large volume injections. So we're talking like 25 microliters, 50 microliters of sample, where at that point you are venting out the solvent and just trying to get the analytes on a column. So it gives you a lot of flexibility. So when we choose inlets, and obviously right now you're probably thinking, well, yeah, splitless is probably going to be the kind of the go-to inlet, and it is really for just about anything. But one thing we do have to keep in mind now is liners. So these inlets, the splitless multi-mode, the packed inlet, again, that has a small sleeve in it, and the PTV, all use liners in them, and each liner has a different volume capacity that we have to be mindful of depending on what our sample is. So what the glass liner is meant to do is to provide an inert space or surface to basically volatilize your sample. And in doing so, as I mentioned, that the liners have different designs to them that either increase or decrease the vapor volume that they can accommodate, and that's really important because based on your solvent type, your injection volume, your column head pressure, and the temperature of the inlet, we can have varying volume expansions of just our solvent, which is going to make us efficient and effective or not. As you can see here, at a normal inlet temperature of 250, and actually maybe a little high of an inlet pressure of 20 psi, as you look at hexane, it expands to 140 microliters, acetonitrile 350. But if you look at the water, and this is a very common one these days, water itself expands to over a milliliter of vapor volume within the inlet. And so we definitely, if you're doing a water-based sample, we really have to be mindful of these conditions, the liner and everything else, so that we make sure that we don't have an issue. This exceeds every liner that we have. So this is what we would call backflash. And we're going to get a lot more into that here in the next few slides, after we kind of explain a little bit more of the liners. So choosing liners, we have, as I mentioned, the volumes of them. There's different treatments or deactivations. We have our standard adjuvant deactivation. We have now our ultra inert deactivation. Other companies have other named deactivations I'm sure you've heard of. They do have special characteristics, glass wool, a cup, tapers, helix, all these different things, and they all have a purpose in how they treat or react with or interact with your sample. So you want to consider, all the aspects of the liner to make sure you're going to get the best chromatography, because again, they all are going to play an important role in getting your sample onto the head of the column, and that's one of the key things obviously with the inlet itself. With that, we want to, as I mentioned, starting off, if we're using a splitless inlet, there are liners specific for split injections, and there are liners more specific actually for splitless injections. So we want to choose a liner that's going to be appropriate for that in developing a method. So if you're starting out with a new method, new application, you may, like I mentioned, I would highly recommend starting in split mode. You may end up changing liners if you go down to splitless, which is fine, but you also can't, if you're doing a split injection, you can't flip-flop different styles of liners under the same conditions and expect to get exactly the same results, because those, again, the glass wool, the shapes, the sizes of the liners actually do change a little bit, and that's all going to have an influence on your sample and how it's treated through the inlet. This is one of the key things I mentioned, the volume. We want to make sure that we're choosing a liner with enough volume to accommodate the vaporized sample. And again, this is also going to be mitigated by our inlet parameters, but we want to make sure that we're not really kind of choking things out initially. We want to make sure that we're more accommodating as we develop the method. Again, we can get it started, get our chromatography looking good, and then dependent upon what our needs are, we can always kind of fine-tune it by changing liner types and inlet modes and things like that. I mentioned backflash, and this is if the vapor volume of the sample exceeds the liner volume, you get backflash. And what ends up happening is, your sample will exceed the volume of your inlet, and actually put the sample back outside of the inlet, where it's a little bit cooler, in the carrier line supplying the inlet, and out the split vent line, even if you're in splitless mode, and parks it right outside the inlet. Again, where it's nice and cool, it allows things to condense. So, sometimes maybe if you go behind and, you inject a standard and then you inject a blank, all of a sudden you see your peaks. More than likely, it's because you had some type of backflash, and your sample is vaporizing, volatilizing in the inlet, exceeding, even on a blank, exceeding the volume of the liner and the inlet, going out, redissolving some of these things. It cools the inlet ever so slightly, so it creates a minimal, a little bit of a vacuum and pulls things back in there. So typically, if you're seeing your analytes on blanks, it's because you have some, again, have experienced some type of backflash at some point in time. And maybe we need to either go in and address that, clean things up one way or the other, or just keep doing, blanks essentially until you get rid of things. Our liners are primarily 2 millimeter or 4 millimeter. These would be 2 millimeters would be more appropriate for a headspace or a purge and trap, basically just providing a throughput and not a volatilization area for or volume for your sample. Our liners are 7 to 8 millimeters long. They're either going to be 6.3 millimeters on the OD or 6.5, depending if it's split, which would be 6.3, or splitless, which is 6.5, because in splitless mode, again, we want to make sure that the sample, the key is to get all the sample onto the head of the column, so we want to really occupy the whole inlet if possible. And the 6.5 millimeter OD liner does that a little bit more, obviously, than the 6.3, which provides an easier flow path for the split flow to go back out the split bed. Recommended injection volumes are going to be 1 to 2 microliters for organic solvents and half a microliter for water. Typically, and not in all instances, 0.5 microliters is okay. You don't have backflash. Some certain circumstances, you still may actually reach backflash with that. And how do we determine that? Well, we have a pressure flow calculator that is downloadable from our website, and some of you may have that already. I think if you get new systems, it's part of a Agilent Utilities menu on there. You have a whole bunch of different calculators that come in there. And again, here I put the link to that to get that. This is our older version. This is the one I have on my PC still. So this is the one I put in the talk. And the newer one is not, say, a single screen for these. You have different icons on your desktop, one for pressure flow and one for vapor volume, but they have exactly the same function. So to determine what our inlet pressure will be, we take the dimensions of our column. So we have a 30-meter column with 0.32 ID in this instance. Typically, with any method, you want to generally start initially anyway with a relatively cold inlet oven temperature. Again, we want to have the sample go through the inlet and focus and condense on the head of the column. So I put here down at 50. I personally chose velocity. And if you call in and speak to myself or one of my colleagues, we will generally direct you to paying attention to velocity instead of flow rate, just because velocity can be used with any dimension column, where flow rate is going to be more dependent on the ID of the column. So in general terms, it's a lot easier to talk about velocity. So I chose helium as my carrier gas. I put it in PSI. I chose a middle-of-the-road velocity, and we give the kind of the optimum range here. We'll discuss that a little bit later too. So I chose 30, and that gives me an inlet pressure of 8.6 psi. And just to show you that the newer version, this is the newer version of that thing, that it does exactly the same. Again, put your column dimensions in, starting oven temperature. I have my average velocity of 30, inlet temperature 250, and it gives me 8.6 as my inlet pressure. So then I take that over to the vapor volume calculator. So I had 250 as my inlet temperature. I'm going to inject 1 microliter. There's my inlet pressure, 8.6. I chose my liner, so I'm going to do a split injection. So I chose a split liner. So that's this 51834647 gives me the vapor volume or capacity of the liner, which is 850 microliters, and I chose methanol as my solvent. And under those conditions, you can see that 1 microliter of methanol expands to almost 670 microliters of vapor volume. And this little key thing here gives me that I'm at 79% capacity of the liner. So I should be safe, shouldn't have any issues with backflash. Under those same conditions, again, 1 microliter, 250 inlet, 8.6 psi, I chose water instead. You can see that I'm going to have a serious problem because I'm at 176% capacity of the liner. So this is a severe case of backflash, and this is going to be very, very problematic. So if you are doing water or need to use water as your solvent, what can we do? Well, we can cut it in half. We chose half a microliter, and under these conditions, we're okay. We're only at 88% capacity of our liner. Now, that may be fine and dandy, but what happens if you need the sensitivity? So you need the 1 microliter. This is where we can actually use some of the functionality of the inlet, and we can do a pulsed injection. And what you can do with this is, going back here, this is the half microliter injection again. I was okay with 88% capacity. So what I did is I increased my inlet pressure. So now you can see we're almost at 32 psi to get the same percent capacity that we're utilizing. So if I do a pulsed injection, I would need to pulse it at 32 psi to enable myself to inject 1 microliter of water. So again, this is a very, very useful tool just to get started, just so you know upon get-go that you're at least not going to have backflash issues. So again, I would highly recommend utilizing this and downloading it if you can. Or again, if you've gotten a system in the last year or two, you should have a disk with these tools or utilities on them. Liners and deactivation treatments. Again, we talked about this already, so I will skip over that. Again, it's just going over deactivation. So here's more of the characteristics. We have a taper. This helps focus the sample as it comes in. So the syringe needle comes down, your sample is vaporized here, and of course you want it to go onto the head of the column. The column comes up into the bottom part of the inlet, or excuse me, on the liner. So if we have a taper, it's get a little bit more focused on that. We have dual tapers. Again, glass wool. We have glass wool here. We have on some liners we have it low. Again, there's a lot of verbiage on this, but this is all for your reference. So I'm not going to go into all the different kind of characteristics of these liners. Other ones that aren't mentioned on that page, again, are baffles, spirals, helixes, things like that. And they're all, again, there to provide some type of surface that will be a little bit turbulent for the sample, so you get better mixing of the sample, a little bit more heated area for surface area for the sample to volatilize and vaporize on and get onto the column itself. So here would be some split injection liners, and you can see this one has glass wool in it in the middle. Again, generally with a higher flow rate through the inlet, you want glass wool in the middle. So in split injections, that's why you're going to typically see glass wool there. This one has a taper. This one does not. So this one is going to allow your sample to have more contact with the gold seal at the bottom of the inlet. This one has a glass nub. That's designed to keep the liner off the bottom of the gold seal and just helps facilitate the split flow. Again, being able to go out and around the liner and out the split bed. Splitless injection liners. Again, these are going to be the 6.5 OD liners. So you have a single taper. I mentioned glass wool at the bottom. So this will help with some of the less volatile components in a sample with a splitless injection. Again, dual taper. This will actually provide a little restriction at the top. So you help minimize backflash, though it does also minimize or drop the volume, the vapor volume capacity of the liner itself. So again, it's just some of those things that you need to be mindful of. With the glass wool, this has been an issue going back and forth, kind of I wouldn't say an argument, but glass wool can be problematic. You know, if you pack your own liners, I would say a lot greater chance of it being actually problematic, and in part because the amount and size and placement actually needs to be consistent so you have consistent results. So if you have, in one instance, you know, really densely packed amount of glass wool, you actually can change the restriction in the inlet and slow the flow rate through your column, and you can actually have retention time shifts just due to your liner and specifically the glass wool in there. If you're packing them yourself, and this is actually true with a lot of manufacturers as well, is that we'll take a liner, deactivate the liner, we'll take a vat of glass wool, deactivate the glass wool, and then we'll break off some of that glass wool and shove it into the liner. Well, when you do that, you have active sites all on those fibrous ends that are now not deactivated because they were, you know, broken off. So typically what's really ideal is actually deactivating the liner with the glass wool in place. And that's what we actually do with our ultra inert liners. So that takes away any of those small active sites, again, on those fibrous ends of the glass wool. So again, all these things you really have to kind of consider and think about when you're developing a method. Again, more reasons or justification of why we have glass wool near the top of the liner or near the bottom of the liner. Again, near the bottom, this would be more for splitless injections. Near the top, this would be more for split. So then, hopefully we've kind of got an idea or grasp anyway of how to at least attack choosing a liner. We may not choose the best one initially, but you know, there's a lot of variation, especially when we're developing a method anyway, because you know we can get our chromatography and then really dial things in and get more specific with liners and things like that. One of the other things to consider also, ironically, is the carrier gas, and its function obviously is to carry things through the column and to the detector, but the selection of the carrier gas and as well as the velocity is going to influence our efficiency. And obviously, as well as our retention time, the faster the flow goes through the column, the faster your analytes are going to go through there. But in doing so, we also can lose resolution and things like that. And as you can see here, this is using helium. And as we change, again, I mentioned earlier, we like to talk about velocity. As we change our velocity with this 15-meter, 0.32 millimeter ID column, we actually can see that we're changing our resolution. So sometimes going faster is good, you know, but at the same time, depending on what you're starting out with your resolution, if you have something that's not quite even baseline resolved, and when you go to speed things up, you know, you can lose more of that resolution. Conversely, if you're starting with a high velocity, you can always or potentially drop it down to gain resolution. And when we talk about velocity, there's a reason for that. And each carrier gas type is going to have a specific amount or range of, say, optimum velocity. So if we looked at this Van Deemter curve, and this is basically a curve representing efficiency, so the lower down on the y-axis here we go, the more efficient we're going to be with just the carrier gas, and we go speed up, then this is the velocity range, so going from 10 centimeters per second to 60. You can see that there is a steep curve on this side. So what ends up happening is if we go too slow, so we're trying to get a lot more resolution by playing with the velocity, if we go too slow, we can actually lose efficiency rather quickly. We get excessive diffusion, we get broader peaks because we're not really pushing the molecule cloud, if you will, through the column fast enough to keep them all together. But if we look at the bottom of the curve here, where we're going to get the most efficiency across here is going to give us our optimum velocity, and then we can go out faster and not lose efficiency as quickly as we would go, say, the same distance or velocity drop on this side. And this is what we call our optimum practical gas velocity. So again, UOP, maximum efficiency, and then this is going to be our maximum efficiency per unit time. So we're really thinking about analysis time. And usually what that is 1.5 to 2 times the optimum velocity for carrier gas. So for helium, that's going to be 20 centimeters per second. So our optimum practical gas velocity is going to be roughly, the range is going to be between 20 to 40. But you can go faster than that, obviously. So in choosing your carrier gas type, this kind of illustrates that very well. So with the cost of helium, a lot of people are actually focusing on nitrogen. It's a lot less expensive. It ironically is actually more efficient. As you can see, it's the lowest one here on the curve, but it is also at the slowest velocity. So your analysis time may increase, not always, just depending on what your analysis is, by going to nitrogen, because you have more, to get the most efficiency from the carrier gas. You're at a much, much slower velocity. And as you can see, the curve on either end is also a lot more abrupt. So the faster you go out, the less efficiency you lose essentially really, really quick. The other thing to see here is that helium and hydrogen roughly have exactly the same efficiency. The benefit of hydrogen is, as you can see, it happens at a much higher velocity. So, if your application is great with helium, but your boss is really saying, hey, we need to really cut costs, let's look at our carrier gas because we're going through this, a lot. Instead of dropping back to nitrogen, if you can, consider hydrogen. Because with the same efficiency, so if you like the resolution that you've had, typically switching from helium to hydrogen, your analysis time drops by a third, and you maintain exactly the same resolution throughout your analysis. So that's one of the benefits with hydrogen. As you can see also, you don't have as much loss of efficiency with going faster either. So it's really, really beneficial that way. With our systems, we have two modes of kind of flow control, and this is one thing that definitely confuses people oftentimes. So what actually happens to our flow as our oven temperature increases? Well, the viscosity of the carrier gas obviously is going to change. So depending on if we're in constant pressure mode or constant flow mode, those are the two main ones that we have. We can also program those. You can see here what's going to happen. So if I can get this, so our column temperature is 50 degrees. Our inlet pressure is 8.6 psi. If we keep our inlet pressure, if we're in constant pressure mode, and keep our inlet pressure constant, and we take our oven temperature up to 325. Oh, I thought it highlighted. I apologize. Let me go back here. Actually, let me go back to the other slide. So again, 30 centimeters per second, that's what I like to start with. Our flow rate, our volumetric flow rate is 1.75 mils a minute. So as we, again, go to 325, maintain that same inlet pressure, so constant pressure, our flow rate now has gone from 1.75 down to 0.6 mils a minute. And our velocities drop from 30 centimeters per second down to 19.1. So as you go up, things start to slow down. This can be beneficial, depending, again, if you have your ladle eluters are very, very tight, they're maybe not quite baseline resolved, maybe switching over to constant pressure mode will help because things will slow down a little bit. Maybe they'll actually be able to separate throughout the run. Again, your run time is going to increase, but that may be okay depending on what your needs are. Conversely now, if we're in constant flow mode, again, we've gone from 50 to 325. This time we've actually kept 1.75 as our flow rate. Our inlet pressure goes to 19.4, and our velocity has actually gone from 30 to 41.6. So things speed up. So again, if you have a lot of resolution between your late eluting compounds, maybe being in constant flow would be more beneficial in getting those out a little bit more quickly without losing resolution or anything like that. Because again, typically with late eluting compounds, if you're going to slow things down, your peaks actually may going to broaden out a little bit, and you could potentially lose resolution. So this may be something to consider as well. Another thing to consider, and this actually happens probably more frequently than not, is that because people don't necessarily know about constant flow, constant pressure, or what actually happens when they're developing their method, they don't set their regulator for their carrier gas high enough. So what they'll find is as they're at 50 degrees, everything's fine, their inlet's happy, but as they go throughout the run, they'll find as they get up to 250, 300 degrees, their inlet starts to beep at them, and they get a front inlet shut down. And that may not be due to a leak, but it could be due to whatever pressure your carrier gas is trying to get to onto your inlet. You don't have enough supply pressure coming to the GC to actually reach that. So that's one thing, again, be mindful of. Set your inlet pressure from your regulator, not your inlet pressure, your regulator pressure to 60 or 80 psi, just to make sure that as you go through your method, that you have enough supply pressure so you don't get the front inlets shut down. And again, if you're not aware of the constant flow and what's occurring on the system, it may drive you a little bit batty, and you may think that you have a leak, and you start tearing apart your inlet when it's simply just turning up the regulator pressure. Next thing to consider would be our detectors. And again, I put this in here for reference. So these are all the various different types of detectors. There's actually one or two probably that are not on this list, but these are, again, the most common ones. And I've put on here kind of what they respond to as well as their detection limit. So you can see that TCD is universal, but not very sensitive. And this is going to be key, too, because I've spoken to people quite frequently that maybe want to do permanent gases, but they have an FID on their system. Well, the FID is not going to respond to carbon monoxide or carbon dioxide all that well. You'll get a blip for it, but you have to be at really, really high concentrations because what it really responds to is carbon-hydrogen bonds. So again, that's just one of these things to be mindful of, is that if you inject a sample and you're not seeing certain things, pay attention to the type of detector that you have, as well as the analyte that you're putting through it. Can it chemically respond to the detector? So again, we have a whole talk on choosing the right column, but I'm just going to kind of go over this briefly, just hopefully to give you an idea of what to consider, just getting started. So when we understand the stationary phase, there's basically two types of capillary columns. We have our plot columns, which is a porous layer, open tubular, so we actually have a solid particle layer that's bonded to the glass tubing. Or we have a wall-coated, which is actually more of a polymeric liquid phase that's on there. So this would be more suited for gas samples, because what we can do with the solid particles will retain the gases, whereas the liquid phases will not. Again, kind of going back to the permanent gases, spoke with somebody that had an HP5 the other day, which is a 5% phenyl, 95% dimethyl polysiloxane wall-coated column, which has no retention characteristics or interactions with light gases. So what they really would need would be a plot column. So again, just starting off with even if it's the wrong column, but the right type is going to be beneficial for you. With the wall-coated, we have various different types of stationary phases. Same with the plots. As you look at something, I'm in HP5. That 5 represented a 5% phenyl onto a 95% dimethyl polysiloxane. That's kind of the backbone of most all wall-coated columns. We do have some that will put an aerolene in there, which does change the selectivity a little bit. Also, it's a little more rigid, so sometimes you'll have less column bleed because of an aerolene phase. And then the biggest difference in wall-coated columns that we also have would be a polyethylene glycol, which is a wax column. And as you can see structurally, they're completely different. So their interactions with analytes are going to be completely different. The selectivity interactions that we do have, or that we can take advantage of, are dispersion, dipole, and hydrogen bonding. So that's really what's going to kind of make selectivity and resolution possible. And here I've listed, as the phase, these are the substitutions. Of course, the PEG is 100%, but we'll have varying degrees of trifluoropropyl. This should be a cyanopropyl, phenyl, and methyl. The contribution to what they have is listed here. And again, this is for your reference. And we do have a talk that goes kind of in depth with all of this in choosing the right column. The main thing to do with columns is to try to match analyte polarity. Again, like dissolves like, so that's the best way to start. If you've done that, if you say, okay, well, I got kind of nonpolar things, but I don't have the resolution. Look for unique interactions, maybe with those colluting compounds, that maybe we can find with a phase or slight substitution of a stationary phase that may invoke or pick out interactions between those two analytes. Obviously, use pre-existing information. No reason to reinvent the wheel. And if you struggle to find anything out there, especially maybe on our website, unfortunately, definitely call us or email us. We have a whole bunch of stuff that we can share with you and hopefully help you choose the right column right from the get-go. So again, I know I brushed over the column selection and a lot of these things really briefly, but yeah, selecting a column, that's going to be the most in-depth topic we probably have because there's a lot of variance in that. So that's why I kind of just briefly went over that. So now we're going to take basically all these different components that we, talked about and try to employ them and get some resolution between a sample. And for this this little exercise, we're going to look at 20 different drugs. Primary, secondary, tertiary means. They have a phenyl character to them in most instances. So looking at this and also pre-existing information, I chose my column. I chose it as a DB5, kind of a standard dimension, 30 meter, 0.32 with a 0.25 micron film thickness. Split slit light because that's the most common. Again, I'm going to start with a split ratio or a split injection. Again, to get the best chromatography initially, again, building upon that, I can, if I need more sensitivity, I can always change that. But right now, I'm really focused on, can I get all these compounds resolved? Standard inlet temperature of 250. I'm going to set my FID temperature to 350 because this type of column can go to 325 as the isothermal limit. So you want your detector temperature about 20 degrees above that. So I'm going to do it 350. My carrier gas is helium. I'm starting kind of midway in the velocity range for helium at 30 centimeters per second. I'm going to start with a really, really mild oven program, and this is pretty generic, and this is where I would suggest most people start. Again, something cold so that we can get it to focus on the head of the column. Anything more volatile, we give it 5 minutes to try to resolve from one another. Then we're going to do a really mild ramp at 10 degrees a minute up to the isothermal limit of the column, and we're going to hold it at 5 minutes. We want to make sure that we're not going to have any backflash. So again, I put my column dimensions in there. And this slide may look familiar. Look at the parameters are all the same as what we had seen before. I've determined I'm going to get 8.6 psi inlet pressure. Again, put it in my vapor volume using methanol. We're going to be fine. I got my split liner down here. Again, inlet temperature, my inject 1 microliter. So I'm not going to have any backflash, which is good because a lot of people doing drug analysis can sometimes put a column in there. And had one actually just the other day, they were seeing caffeine. Well, it's not from the column. The column's never made with caffeine. But in any case, we're not going to worry about that now. So I do my 1 microliter injection under that program, and this is what I get. And you can see here we got a couple areas to consider. We got 8 or 9 minutes of just dead time. That's wasted time for me. And we got 2 areas here where we got multiple compounds that are not well resolved. So we got 2 areas that we need to improve upon. So what are we going to do first? Well, the easiest thing, obviously, is to try to get rid of that time and see, ultimately, how it affects the back end. So the first peak comes out roughly about 9 minutes, and then I calculate, well, what temperature does it come out at? So according to my temperature program, here at 50 degrees for 5 minutes, 10 degrees up to 325, my first peak doesn't even come out until 90 degrees. So, well, if that's the case, and it spends a lot of time interacting with that, why don't we start our analysis at 90 degrees? So if we do that, basically all we've done is change our initial oven temperature. 90 degrees, we're holding it for 5 minutes. Again, the same ramp, going at 10 degrees a minute to 325 and holding for 5 minutes. We've shaved off 5 minutes of our front, which is good. That saved us time. And in doing so, it's actually helped improve the resolution of these compounds. They're still not perfect, but they're improved upon. So if 90 was good, we can bump it up a little bit. We don't want to go too have them come out too fast. So I'm going to start at 100 degrees for 5 minutes and do the run. And this is what we're getting. It's still affecting these, but not that great. Excuse me. I'm fine with my initial run time here at roughly about 3 minutes for my first peak. That's good. I'm not wasting, the initial 9 minutes. Everything else up to this point looks good, but now I have to really spend more time on resolving these. So how am I going to do that? So one of the best ways to do that, or first things to try anyway, to resolve coelutions is add a hold at 20 to 30 degrees below the elution temperature of those peaks. So my coelutions occurred at 10 minutes, which is great, seeing that my first peak didn't even come out till 9 minutes, so I've really pushed the back end of my run up quite a bit. According to my last oven program, my coelutions occur near 150 degrees, so I'm going to set a hold 20 degrees below that at 130. So as we do that, I got a 100-degree hold for 5, so I didn't change anything up front. We're going 10 degrees a minute up to 130, and then we're going to put on a hold for 5 minutes at that. And then after that hold, we're going to continue with our ramp up there. And as you look at that, if we zoom in now, we can actually see, I think, that we have baseline resolution now of our last compounds. So in this instance, it worked. It doesn't always work. Sometimes we at that point, we actually have to change the selectivity of the column. But if you do have coelutions with a column that seems like it should be appropriate for your analysis, again, putting that hold 20 degrees below the elution temperature of those compounds will certainly give you a shot at getting those compounds resolved, because we're slowing things down and giving a little bit more time for those analytes to interact with the stationary phase, and hopefully something unique about one of the molecules versus the other is going to allow for this or enable this the resolution to occur. So conclusions, and I know again we went through this really quick. The first thing obviously is think about your sample and your complete sample, not just the analyte that you're interested in. Look at the sample composition, your matrix, and things like that, because we have to consider all of that from your analyte of interest. We want to make sure that the column can accommodate the type of sample, and that we make sure that we're getting enough retention and resolution between what you're interested in as well as whatever else is in there. And of course, is it chromatographable by GC? Are you going to have to derivatize things? Are they thermally stable? Are they even, the volatility aspect of it goes to potentially derivatizing it. If we can, some type of sample cleanup. What kind of level of detection do you need? Can you use a TCD, or do you need a mass spec or something more selective that gives you even better sensitivity? And then when looking for your application, use the information sources that are already out there. A lot of things obviously have already been done. Don't reinvent the wheel. Utilize technical support. We can definitely help choosing a column for sure. You always want to start typically with a mild oven program, just to get things on there. Make sure that you're seeing all the compounds, that you aren't having any negative interactions with say a functional group or an active compound with a particular type of column. And again, utilize technical support. That's what we're here for you guys to gain more information and hopefully be more successful right from the get-go. Again, this is here for your reference. And this is true not even just for the DB5 column we're using this illustration, but basically for anything, a mild oven ramp to the isothermal limit of the column. Start midway with your velocities. If you're using helium, 30 centimeters per second, hydrogen, 45. I didn't include nitrogen, but if you're using nitrogen, probably 16 to 20 would be appropriate for that. So again, this is kind of your guidelines, if you will, for starting parameters for getting a method just going. Some additional resources for sample prep. We have different application guides and catalogs and things like that have a lot of valuable information for treating samples. So again, this is here for your reference. And then, again, I'm going to reiterate it a lot. Utilize technical support. Again, that's what we're here for. If you want to call in, it's through our 800 number. Unfortunately, everything is based off the 800 number. But if you want to get over to GC Columns and Applications, it's 33-1. If you want to talk to our sample prep folks, it's 33-3. We're all interlinked, so we chat back and forth, so we can, if you have questions on both, we can accommodate that. Or, if you would rather just send some questions in to our email boxes, I've provided those here. Yes, we still do have a digital fax, although I assume that's probably going to go away soon. So again, you could fax things in if you're not able to print them out. And with that, we went just a little bit over. I do hope that you guys found today's presentation useful. Again, I know I bombarded you with a lot of things, went over them kind of briefly, just hit the surface on things. But again, what I wanted really was to make sure that you thought about every aspect along the way. It's not just, hey, I got this box and a column, and I got the sample I want to inject. There's a lot of things really to consider in developing a method for this. And again, utilize technical support. And with that, I want to thank everybody for attending today.
And we want to thank you, Simon, for a very informative and extremely helpful presentation for our audience. And before we go to our Q&A session, which will happen next, we do have a brief polling survey concerning today's presentation. The poll is now open on the lower right side of your console. While the poll is optional, we do ask you to complete each question, and thank you for taking the time to answer this survey. We value your opinions on how Agilent can better serve you, and we welcome your feedback. And as you are completing the survey, I will remind our audience once again that you may ask questions in one of two ways. You may put your questions in the Q&A box addressed to all panelists. Well, I will read them, and Simon will answer them. Or if you wish, you may ask questions over the phone line by pressing *1 on your touch-tone phone. The operator will open your line. If your question has already been answered, or if you wish to remove yourself from the queue, please press the # key. All right. Since we do have quite a few questions, I am going to move right now to the Q&A box, Simon. And the first question is, I have, and I'm sure this is also in your Q&A box, Simon, I have the same method, same column on both sides, A and B. There's two components elute together and won't split on the A side. I tried all flow and column pressure condition changes, and nothing helps. Do you know the reason for my problem?
Yeah, something's got to be different, and it could actually be a result of the column at that point. But what we would need to do is really compare, retention times. Obviously, the oven program's the same and things like that. But what can happen is because, if you put in 1 milliminute or 30 centimeters per second on, your front detector and do the same on your back, your front inlet and do the same on your back inlet, your velocities through those two columns are not going to be the same. I will almost guarantee it. The system doesn't measure that. All it does is calculate a pressure, and it measures the pressure, but it's based on the dimensional tolerances, what is truly your column dimensions. And so slight variations, and there are tolerances in length and ID of columns, that can actually have a result on the flow rate or the velocity through the column. A small change like that, I'm going to assume that on the B side where it's working, they are barely resolved, because if you've played already with your flow rates and things like that, you should have been able to resolve the resolution on the backside, trying to basically match things up. So this would be one where I definitely would want to take a look more of your chromatography and your parameters and see really what is the difference. Another thing it could be is just a buildup of residues on the front end of the column, maybe more so on the A side than the B, and those two analytes are interacting with that to a greater degree than they are on the other column where maybe that residue is not present. So there may be a few things going on with this. This would be one of those instances I would definitely recommend either emailing it in to the GC email box or calling us in, and again we'll have you send probably send the information to us directly at that point, just so we can take a look and see what's going on and see maybe if you do have a column issue or if it's just some little nuance of the system itself that maybe we can help get them both functioning properly.
Thank you, Simon. And here's a question from the chat box. What should be the liner and liner volume if we use sample injection valve for gas sampling, freons? We use low, we use low and high sample volume like 25 microliters and 1,000 microliters. And
the question, I see.
I don't think you can see this, Simon. It's in my chat box.
Oh, okay.
I will read it again. What should be the liner and liner volume if we use sample injection valve for gas sampling? And apparently they use freons. We use low and high sample volume, like 20 microliters and 1,000 microliters.
With that, if you're using a gas sampling valve, again, you're already injecting a gas. You don't have to worry about the sample itself vaporizing and the volume itself expanding. So really at that point, again, your inlet is more of a throughput. So something like that you would want to use more of a 2 millimeter or a 1 millimeter ID liner just to get it, again, moved from the sampling valve of the sample loop at that point onto the head of the column. So if you're using a split split inlet, I would go typically a smaller ID liner just so you don't go, from a narrow tube basically feeding into your inlet all of a sudden to a really broad tube, your liner at that point if you're using a 4 millimeter ID, where things can kind of disperse and then focus back onto the head of the column. You want to kind of keep things nice and tight, so a smaller ID liner is what you'd want to use in a situation or a sample like that.
Thank you, Simon. And ladies and gentlemen, before we continue, I do have a few announcements since many of you have requested a copy of the presentation. Following the seminar, you will be receiving an email with a link for the recording, as well as a link to our library for a PDF copy of the presentation. In addition, you will be receiving a 25% discount coupon for purchase of Agilent columns. And as we are circulating the slides presently being displayed, it will tell you a little more about our coupon offer and any restrictions that do apply, as well as information on technical support. However, this is also part of the PDF, so you will have this information in hand. All right, let me continue going to the Q&A box. This is another question, Simon, that is in the chat box. And, of course, it's complicated, but I know you can handle this. What minimum and maximum velocity can we set with H2 as carrier gas in constant flow mode?
One of the nice things I had mentioned earlier as kind of explaining constant flow versus constant pressure, when using hydrogen as your carrier gas, your inlet pressure is about half of what it is with helium. So one of the things is, you don't have to necessarily worry about your inlet pressure nearly as much, at least as a supply thing. For the carrier gas velocities, I would say probably on the low end with hydrogen, maybe 30, 35 centimeters per second. And then on the upper end, you could go as fast as you want. There really is no limitation apart from how it affects your resolution of your compounds. The inlet itself is going to be able to handle it. We know that, if you have a leak in there, that you're going to get a front inlet shutdown. It's going to shut the gas supply off at the back of the GC. A lot of people do worry about hydrogen as a carrier gas, which is a little bit of irony here. A lot of people worry, or their health and safety folks in particular, worry about 1 or 2 mils a minute of column flow, but they don't worry about 40 mils a minute going at your FID. and that can be more of an issue. If your column breaks, you can get hydrogen back from your FID into your GC oven, which is where everybody kind of freaks. But it's actually really, really, from a safety standpoint, really, really difficult to get hydrogen built up to an explosive capacity. Typically, especially if you're going to get an inlet shutdown, your oven's going to open the flappers. It's going to cool things down. It's going to blow all that hydrogen out if there is some type of leak. And even with that, it's hard to maintain the 4% amount of hydrogen in the GC. That would be problematic. And then even with that, the GCs, basically that door is explosion proof. So that's why as you shut the door on our GCs, they kind of have that spring latch. So that wouldn't be something not to be concerned about. So yeah, go as fast as you want. Don't worry about things. There is really no limitation to what you can do short of the biggest limitation would be